In this session, you are going to use correlations to calculate heat transfer coefficients. Correlations for external flow are given in Table 7.9 for different geometries and conditions. You should consider both of these carefully before choosing the correlation to use. You should choose a Nusselt number correlation, as you can use this to calculate the heat transfer coefficient, which is equal to the Nusselt number, divided by the characteristic length, times the thermal conductivity of the fluid. You usually need to use the average Nusselt number, to give the average heat transfer coefficient. Multiplying the average coefficient, by the total heat transfer area of the plate, and the temperature difference, will give you the total heat transfer rate from the plate, Q. You can use local correlations, to calculate the heat flux, for a given value of x, i.e. for a given position on the plate. For a cylinder, you are only given a correlation for an average Nusselt number. You would have expected a lower, and higher, Nusselt number at the front, and in the wake, of the cylinder respectively. Three correlations from the table are highlighted here. One of the conditions specified in these, is T, F, which is the film temperature. As you saw in a previous session, the film is the boundary layer, where temperature decreases from Ts, to T infinity. Hence there is an average temperature in the film, halfway between these temperatures, and this is known as Tf, the film temperature. You need to use the film temperature, to obtain the physical property values, needed to calculate the Reynolds number. You also need to determine the value of the Prandtl number, PR, at Tf. If you look at the correlation for the cylinder, you will see that it contains two constants, C and M. The values of these constants depend on the Reynolds number of the fluid flow, and can be obtained from Table 7.2 as indicated. More correlations are presented in this slide, including those for cylinders, spheres, and tube banks. You should read the fine print of the table. For the one correlation, you should use the average temperature, not the film temperature. Note that the surfaces for these correlations are at a constant temperature. Correlations for internal flow are presented in this slide. The characteristic length, used in calculation of the Nusselt and Reynolds numbers for circular tubes, is the internal diameter. As with external flow, the fine print at the bottom of the table contains important information, and you will be informed about 3 bits of this information. For most Nusselt correlations, you need to use the mean temperature of the fluid for the variables in the Nusselt, Reynolds, and Prandtl numbers. If you are doing calculations for a long pipe, you need to use the average mean temperature for the pipe as shown. Most of the correlations are for fully developed flow, except for those that specify an entry length condition. The correlations for fully developed flow can, however, be used for long tubes with L divided by D greater than about 10. The fully developed region will then be much longer than the entrance region, as you can deduce by inspecting the diagram of flow inside a pipe. If you have to deal with a non-circular tube, such as one shaped like an equilateral triangle, you need to use the hydraulic diameter, as the characteristic length in the Nusselt and Reynolds numbers. The hydraulic diameter is 4 times the cross-sectional area, divided by the wet-head perimeter. The area of a triangle is half base times height. In the diagram, the base has length, s, while the height may be determined from Pythagoras' law. The wet-head perimeter is the length, in the cross-section, where the fluid touches the tube wall. You can see that the fluid touches all 3 walls of the tube, so the wet-head perimeter will be 3 times s. Note that some correlations are for a uniform heat supply per unit surface area, denoted as uniform Q double dash in the table, e.g. 1000 watts heat supplied, per square meter. Other correlations are for a uniform surface temperature, Ts, e.g. 400 Kelvin, all across the surface. Also note that, if you are dealing with a liquid metal fluid like mercury, you will need to use correlation 8.65, or 8.66. And this brought you to the end of this session's slides.